Okay, so we were discussing about the temperature variation in ammeters. So how can we minimize the error caused by such temperature variations in an ammeter? One thing is that we have to make the shunt material and the meter movement material, the coil, the same. That is, the copper should be the material of the shunt. Okay, because we cannot make the copper winding, the winding of the meter as aluminum winding. It should be copper. So only choice is that we have to make the shunt resistance also copper. But the thing is that copper is a little bit costly and it makes the system more or less bulky. Other thing is that the two resistances, one the meter as well as the shunt, are in two different places. So at two different places, the temperature variations may slightly vary. At two different positions, at two different locations, the shunt and the meter movement resistance may vary slightly, and that slight variation can also bring in errors. So that is not a feasible solution. So the only feasible solution is to add a 20 to 30 times higher resistance, that is a swamping resistance, in series with the meter movement. Okay, that is, this is a swamping resistance which is 20 to 30 times more than the resistance of the meter, that is Rm. Okay, and in that way the major portion of the resistance, this is a series combination, major portion of the series combination will be made by the material magnanin. Okay, only a small portion of resistance will be made of copper, and this is magnanin itself. So we can tell that these two branches more or less have the same material, because this branch is having majority portion as magnanin, because the copper forms only a small portion of the winding. Okay, so small portion of the resistance, other majority of the resistance is actually the magnanin material. So we can tell that these two branches are having resistance of the same material. Okay, now how can the swamping resistance reduce or minimize the error caused by the temperature variation? It is very easy to understand, or it is very easy to understand by having a numerical. So just go through this example. I'll just go through the example. That is, we have a moving coil instrument whose resistance is 25 ohms. So what is this 25 ohms? A moving coil instrument whose resistance is 25 ohms mean that Rm is equal to 25 ohms gives a full scale deflection with a current of 1 milliamps. Okay, so that means Im is 1 milliamps. That is, the current flowing through the basic movement is 1 milliamps. This instrument is to be used with a magnanin shunt to extend its range to 100 milliamps. So what should be the total current? I is equal to 100 milliamps. So all three materials are given, data are given, that is Rm is equal to 25, Im is equal to 1 milliamps, and total current I is equal to 100 milliamps. From these two readings we can get the value for my ISH, that is 99 milliamps. Calculate the error caused by a 10-degree rise in temperature when copper moving coil is connected directly across the magnanin shunt. That is, there is no swamping resistance. Without swamping resistance, we have a shunt magnanin resistance as well as the basic movement only. There is no swamping resistance. What happens to the error? What is the error when there is a 10-degree rise? What is the second case? We have a swamping resistance connected in series with the moving coil. What is the resistance of that swamping resistance? It is 75 ohms. See, the resistance of the basic movement was 25 ohms. See, the resistance of the swamping resistance, it is what? 75 ohms. Okay, so 3 times. So we will see the first case. So we have to first get the value for m. M is nothing but I by Im, that is 100 by 1, that is equal to 100. Now what is RSH? Again the basic equation, Rm by m minus 1. We have Rm as 25, 100 minus 1, that is equal to this. This is the value for RSH. And then we have to get the resistance of the movement with increasing temperature. Now there are two more data given. That is, the temperature coefficient of copper is 0.004 per degree Celsius, and that of magnanin is 0.0015 per degree Celsius. So basically for the first thing, we have the shunt made of this material, and the movement is made of the material copper. Okay, so the basic, whenever we have to make the calculation of increase in resistance of the basic movement, we have to use this data, and whenever we have to make the increase in temperature with respect to 10 degrees Celsius for a shunt or for a swamping resistance in the second case, we have to use this data. Now, we can tell that this is Rm is equal to Rmt is equal to 25 into, that is the original resistance multiplied by 1 plus alpha into T. So what is my alpha? Alpha for copper is 0.004. How much is my temperature rise? That is from 0 it is rises to 10 degrees Celsius. So T is 10 here. So substituting that, we'll get it as 26 ohms. Okay. Now, what is my shunt resistance when there is a temperature rise of 10 degrees Celsius? That is, initially my resistance was, shunt resistance was 0.2525, and that is substituted here. 1 plus, there is a temperature rise of 10, and what is the temperature coefficient for McNannon? It is 0.0015. So my resistance is this one. Okay. Now, so we'll get my from these two values. We'll get the increase in meter current, the basic movement current. Initially it was only Im, that was 1 milliamps. What happens to Im when there is a 10 degree temperature rise? That is Imt is equal to, what is the current divider rule? Current divider rule is the total current multiplied by the resistance of the opposite branch divided by the sum total of resistance. So what is my resistance of the opposite branch? Resistance of the opposite branch is that of the shunt resistance, since I am calculating the current through the meter. Okay, so that is the resistance of the opposite branch, that is the shunt divided by 26 plus this value, that is, it is 0.963 milliamps. So initially it was, the without temperature rise Im watts was 1 milliamps. Now with the 10 degree rise we have the value as 0.963 milliamps. So what is the error? Error is equal to actual value minus true value divided by true value. True value is 1 itself, that is why there is no denominator here. So 0.963 minus 1 divided by 1 into 100, that is minus 3.7 degree, minus 3.7 percentage. Now you take the second case. With respect to Rm, there is only one change, that is Rm is added with a swamping resistance of 75 ohms. So 25 plus 75, that is 100 ohms. Okay. So we'll substitute the value for Rm here and get the value for RSH. RSH is equal to Rm, which is 100 by multiplication factor is the same, because I by Im, I is 100, Im is 1. So that remains the same. So 100 minus 1, that is 1.01 ohms. Same procedure will follow. That is, we calculate the resistance of Rmt, that is with 10 degree temperature, but there is a change here. This is actually for the copper. That is copper. Initially the meter is having a resistance of 25 plus 1 plus 10 into 0.004 plus, then I am adding a swamping resistance of 75 plus 1 plus 75 into 1 plus 10 into this swamping resistance is made of McNannon. So that is 0.00015. Okay. From this we'll get the overall meter resistance with 10 degrees temperature rise as 101.11 degrees Celsius. And what about the shunt resistance with 10 degrees Celsius? That the initial value is 1.01 multiplied by 1 plus 10 into this value. We'll get it as 1.0115 ohms. So again the same procedure, applying current division rule, that is total current into the resistance of the opposite branch, which is this value, divided by the sum total. Okay, so that is the sum total here. We'll get it as 0.9905. Initially it was 0.963 milliamps. Now it is increases very close to 1 milliamps. Okay, so obviously the error reduces. Error initially it was minus 3.7 degree percentage. Now it is reduced to minus 0.95 percentage. So this is how the error get reduced by adding a series swamping resistance with the meter resistance. Okay, now this is a case of ammeters. Now this basic movement can be, so this is actually for the multi-range ammeters. You can have several shunts. This is one shunt. If this is this which is connected, this selector switch is connected to this portion, this much resistance will be added. If the selector switch is connected to this point, this much resistance will be added. If the selector switch is at position 3, only this much resistance is added. So R3 is different from R2 is different from R1. So when shunt resistances varies, obviously the range of the meter also varies. So this is how you get a multi-range ammeters. Okay, you can just go through that. Okay, And for getting multi-range ammeters, you will have three. Here in this example, it is having three range ammeter. It's a three range ammeter. So if it's a three range ammeter, you will have three different multiplication factors, that is M1, M2, and M3. The calculation of M1, M2, and M3 remain the same. You can just go through these set of readings. The same one, RSH1 is equal to Rm by M1 minus 1. Same thing. So what is M1? I by Im1. Okay. So likewise, we can get the values for M1, M2, and M3. Okay. So you just go through that, and you can just understand that. Okay. Examples are also given here. Okay. You can just go through that. Simple substitution examples only. Now we'll go to the voltmeters. So the basic thing can be added to. Basically, we can convert the de-Arsnoval galvanometer or the basic moment to a voltmeter also. Voltmeter also they remain the same. For converting a basic moment to ammeter, we had a shunt multiplier. Okay. Now converting a basic moment to a voltmeter, we have a series multiplier. That is only the difference here. So instead of RSH, we have an RS connected in series with my basic moment. Or this will have the basic moment can accept only maximum 25 millivolt across the basic movement. It can accept only 25 millivolt across the basic movement. So what if we want to measure more than 25 millivolt? There are cases, in many cases we have to measure more than 25 millivolt. In that case, we have to connect a series multiplier in series with Rm to convert this basic movement to a voltmeter. So we can measure any voltage V by having a series multiplier. Okay, so there is a small derivation here which is the same, that is same as before, that is it's a series connection. So these are the literals explained, that is Im is equal to Ifs, that is a full scale deflection current of the meter. Rm is the internal resistance of the basic movement, and Rs is a multiplier resistance, and V is a voltage across the meter movement when a current of Im flows through that coil, and V is a full range voltage of the meter. Okay. Now the small v is the voltage drop across the basic movement, which I told as a 25 millivolt maximum, that is Im into Rm. Okay. So what is my total V? Total V is nothing but there is two resistances, that is Rm plus Rs. So when Im current flows through this total resistance, that will create my total V, that is Im into Rm plus RSH. From here, we get the value of Rs as V minus Im Rm by Im. V minus Im Rm by Im. Okay, that is V by Im minus Rm. Okay, now for an ammeter, what was my multiplication factor? For my ammeter, multiplication factor was the total current I divided by Im, or Im was the current through the basic movement. Okay, now here the multiplication factor is almost the same, that is instead of the total current I, we have the total voltage V, and what is small v? Instead of Im was the current through the basic movement, small v will be the voltage across the basic movement. So capital V by small v is equal to, what is capital V? We substitute the values. Capital V is Im multiplied by Rm plus Rs, and what is small v? Im into Rm. Cancelling the terms, we'll get as Rm and Rm get cancelled, 1 plus Rs by Rm. From here we get the value for Rs. There also we calculated the value for RSH. What was RSH? RSH is equal to Rm by m minus 1. Here it is Rs is equal to m minus 1 multiplied by Rm. So this is how. So for creating another range of a voltmeter, you have to select a series resistance. Okay, so this is a equation which will get the value for the series resistance. Okay, now there are also qualities for the construction of multipliers which remains almost the same, and here also for minimizing the variations due to temperature, you can add what? A swamping resistance. Okay, a swamping resistance in series with the multiplier as well as the basic moment. Okay, here also you can see example 9.12. Just go through that example 9.12 and you can see that the swamping resistance will minimize the error due to the temperature variations. So these two classes we have discussed, ammeters, then swamping resistances, voltmeters, and everything. Okay, thank you.